Hello everyone, myself P. Jithendar, Assistant Professor in Electrical and Electronics Engineering, MLR Institute of Technology. So in today's session, we are going to discuss about the transient analysis. So in this transient analysis, we are having the subtopics: transient analysis of series RL circuit, series RC circuit, and series RLC circuit. Also, we are having the Laplace transformation in series RL circuit, RC circuit, and RLC circuit. Okay. So here, for the transient analysis of series RLC circuit, we have to do the derivation part in differentiation method. Okay. So before that, what is meant by transient analysis? So here we need to discuss the following things. So what is meant by transient analysis? So transient analysis is nothing but it is calculates the circuit total response. It calculates the total circuit response over a period of time, and the accuracy of the transient analysis is depends on the size of internal time steps, which together make up the complete simulation time, known as the run to time or stop time. So mainly in this transient analysis of series RL circuit, so mainly we have to calculate the circuit response, if it is a current or if it is a voltage drop at resistor at inductor L. Okay. So mainly we have to calculate the current response of the RL circuit. Okay. So here in transient analysis, so I am taking the one series RL circuit. So before that, here we are having some initial conditions. If time t equal to 0, then current also 0. The initial conditions are if t equal to 0, then time t equal to 0. So now here I am taking the transient analysis of series RL circuit with differential equation. So here I need to draw the circuit first. So here is the RL circuit. So plus minus, voltage is V. So here initially if t equal to 0, then current is 0. So resistor is R, inductor is L. If switch is closed, directly the electrical current is flows through the resistor R and inductor L. So now, so the entire circuit is a series circuit. In series circuit, current is constant, but we are having the different voltage drops at resistor. At resistor R, I am taking the voltage drop as a VR. At inductor L, I am taking voltage drop as a VL. Right? So now, at resistor R, the voltage drop VR is equal to I into R. At inductor L, VL is equal to L into di divided by dt. Suppose let us take as this is equation 1 and equation number 2. So now we have to apply KVL. Apply KVL in this single loop. So we'll get plus V minus VR minus VL equal to 0, or we can also write V equal to VR plus VL. Now V equal to, now substitute these two equations in V equal to VR plus VL. Now what is VR here? I into R plus what is VL? L into di divided by dt. So L into di divided by dt. Now this equation we have to write in terms of the differential equation, right? So here first we are having the L into di divided by dt. So first we have to write the differential equation, that is L into di divided by dt plus IR equal to V. Right? So now here take L as a common term here. So L into di by dt plus r by L into I equal to V divided by L, right? So we have to take as a common as a L. So L into di by dt plus I into R by L, that is equal to V. Now the equation is like this: di divided by dt plus R by L into I equal to V by L. Okay. So now here, now in this equation is look like di by dt plus pi, that is equal to q, where p equal to R by L and q equal to V by L. Now we have to calculate the current response of the given series RL circuit. For that, we are having the total current I equal to, so complementary function plus particular integral. By using this equation, we have to find out the total current response of the given circuit. So now the complementary function IC equal to, the equation is C into e power minus integral of p dt, that equal to C into e power minus integral of p. So what is p here? R by L into dt, that is equal to C into e power minus R by L, integral of 1 into dt is t. This is IC value, complementary function value. So let us take as, so this is equation number 3 and this is equation number 4. So now, so IC value. Now what about IP value? So IP equal to, here we are having the equation e power minus integral of p dt into integral of q into e power e to the power of integral of p dt and again dt. So that is equal to e power minus p. So what is p here? Again R by L. R by L into dt into q. So what is q here? V by L. V by L into e to the power of p is R by L into dt into dt. That is equal to, so e to the power of minus R by L into dt is e power minus R by L into t into, so V by L is constant term. So take V by L into e to the power of integral of R by L into dt means R by L t into dt. Okay. So now V divided by L into e power minus R by L into t into integral of e to the power of R by L t is e to the power of R by L t divided by R divided by L. Here L and L get cancelled. So e to the power of minus R by L plus e to the power of R by L get cancelled. So here we'll get V divided by R. So this is V divided by R is the particular integral equation. So this equation let us take as 5. Now substitute equation number 4, equation number 5 in equation number 3. So 4 and 5 in equation number 3. So what is equation number 3? I equal to IC plus IP. So what is IC here? C into e power minus R by LT. C into e power minus R by LT plus V divided by R. So IP value is V divided by R. So this is the current equation. But here constant C is there. So we have to calculate the constant term. So how we can calculate the constant term here? So we are having the initial conditions. So we are having the initial conditions. If t equal to 0, then I equal to 0. Now substitute in this equation. So I value 0, that is equal to, so in this equation, so I value is 0, C into e to the power of minus R by L into T 0 plus V by R. So 0 equal to e to the power of 0 is 1. So C into 1 is C plus V by R, or C equal to minus V divided by R. So this is equation number 6. This is equation number 7. Now substitute 7 in equation number 6. So the equation number 6 is I equal to, so C, what is C value? Minus V by R into e power minus R by LT plus V by R. So I equal to, I am taking as a V by R as a common here. So 1 minus e to the power of minus R by L T. This is the total current response of the given RL circuit, right? So now we have to calculate the voltage drop across the resistor and voltage drop across the inductor. So voltage drop across the resistor, that is VR, equal to I into R. So substitute I value in this equation, R get cancelled. So we'll get V into 1 minus e power minus R by LT, VR value. Now similarly, inductor value. So inductor voltage equation. So VL equal to L into di divided by dt. That is equal to L into d by dt of I. So what is I value here? So I value is V by R into 1 minus e to the power of minus R by L T. So that is equal to L into, so V by R is constant, common term, into, so here, so differentiation, so d by dt of 1, 0, minus d by dt of e to the power of minus R by LT is e to the power of minus R by LT into, again we have to differentiate minus R by LT. So we'll get minus R by L. So that is equal to, so L into V by R into, so minus into minus plus e power minus R by LT into R by L. So L get cancelled, R get cancelled. Now we'll get VL is equal to V into e power minus R by L T. This is the voltage drop at inductor L. Okay. So VL is equal to V into e to the power of minus R divided by L. Okay. So here for the series circuit, the current response I equal to V by R into 1 minus e to the power of minus R by LT, and VR is equal to V into 1 minus e to the power of minus R by LT, and voltage drop across the inductor is VL is equal to V into e to the power of minus R by LT. Okay. So here in this equation we are having the time constant. So the time constant is tau. So time constant is nothing but time taken to reach reach the 63.7% of its final value. Okay, so the graphical representation is like this. So current. So here the graphical representation of the time constant is, we'll get graph like this. So here we are having the maximum value. So we'll get graph like this. So here we'll get 63.7%. Okay. So where tau equal to L divided by R is the equation. Okay. This is about the transient analysis of series RL circuit with differential equation. Okay. So thank you and all.